Hi everyone, my name is Kiarash and I would like to present our work on faster algorithms for quantitative analysis of Markov chains and Markov decision processes with the small Treewidth. This is a joint work with Ali Asadi, Krishnendra Chatterjee, Amir Kavshtar Goharshadi, and Andreas Papagiannis. We will start by giving a quick introduction, revisit some quantitative objectives on Markov chains and Markov decision processes, revisit Treewidth and tree decomposition, and continue by explaining the main idea and the main algorithm of the paper, and finally conclude by demonstrating some experimental results of our approach. Markov chains or MCs and Markov decision processes or MDPs are two standard formalisms in system analysis and verification tasks. Markov chains are used to capture randomness and Markov decision processes are used to capture randomness as well as non-determinism in systems. The main quantitative objectives for these formalisms are hitting probabilities, discounted sums of rewards, and mean payoff. These objectives have not yet been thoroughly studied in terms of parameterized algorithms and parameterized complexity, that being the goal of this paper. We show that these objectives can be computed in linear time if the underlying graph has a specific structural property, that being bounded to Treewidth for the corresponding tree decomposition. We also experimentally show that graphs obtained from control flow graphs of programs have this property, and we can see the efficient runtime in practice. The three quantitative objectives studied in this paper are hitting probability, discounted sums of rewards, and mean payoff. Hitting probability is the probability of eventually reaching a set of vertices starting from some vertex and going through a random walk. In discounted sum, the total reward is the sum of rewards obtained in each step of the process, each time discounted by a factor lambda. In mean payoff, we look at the limit of average rewards per step as the number of steps tends to infinity. Note that in MDPs, we assume that the player aims to maximize the hitting probability or the objective by choosing the best possible strategy. The idea behind the tree decomposition is to decompose a graph into several small parts, which we call bags, such that the bags are connected to each other in a tree-like fashion. This makes it possible for us to do things like bottom-up dynamic programming in pretty much the same manner as in trees. Basically, we can solve problems on trees easier, so we try to transform graphs into trees. Formally, a tree decomposition should satisfy three properties. The first one is that each vertex should appear in at least one bag. For example, you see that vertex number 3 here is present in this bag, and this bag. And vertex number 4 is present in this bag and this bag. The second criteria is that each edge as well should also appear in at least one bag. For example, you see that two edges between vertex number 3 and vertex number 4 are considered within the bag containing vertex number 3, number 4, and number 6. The final criteria is that each vertex should appear in a connected subtree of T. For example, you see that vertex number 3 is present in this bag, and this bag, which together form a connected subtree of T. Or vertex number 4 is present in this bag, and this bag, which together form a connected subtree of T. To give a bit of more intuition, we can see an example of another desirable feature of the tree decompositions. For example, if we remove a bag and all its vertices from a tree decomposition, and also remove those vertices from the initial graph, the produced connected components in the initial graph correspond to the produced connected components within the tree decomposition. For example, if we remove this bag containing vertices 3, 4, 6, and also these vertices from the rest of the bags of the tree decomposition, and consequently remove vertices 3, 4, 6 from the initial graph, we are left with two connected components in the initial graph. The first one being 1, 2, 5, 8, and the second one being 7 and 9. Also, in the tree decomposition, we can see that we are left with two connected components, the first one being 1, 2, 5, 8, corresponding to the first one here, and the second one being 7 and 9, corresponding to the second one in the initial graph. Finally, Treewidth is defined as a number which is the size of the largest bag of the tree decomposition minus 1. Let's try to compute the hidden probabilities in Markov chains. Before explaining the main algorithm, we would like to see how we can use the state elimination trick to solve the problem in a straightforward manner. Assume that we're given a Markov chain C and a target vertex V, and we would like to compute the hidden probabilities of all vertices to this target vertex. So, what is the straightforward way to solve this problem? If our Markov chain has only one vertex, well then there is not much to solve and we do already have the hidden probability, which is 1. Otherwise, we would like to try to remove the vertices one by one and fix the hidden probabilities, maintaining all the hidden probabilities untouched throughout the process. Imagine that we would like to eliminate vertex U with predecessor U prime and successor U double prime. There are two cases for this. The first case is that there is no edge between U prime and U double prime, and the second case is that there is an edge from U prime to U double prime. In the first case, in order to eliminate U, we can simply draw an edge from U prime to U double prime with the probability of P1 multiplied by P2. So finally, we would have U removed and the probability P1 multiplied by P2 added as a new edge from U prime to U double prime. In the second case, where there is already an edge from U prime to U double prime, we can simply remove U and add the probability P1 multiplied by P2 to the already existing probability P3 from the already existing edge from U prime to U double prime. So, in the end, we would have removed U and we would have fixed this probability by adding P1 times P2. This is a neat solution using the state elimination trick. However, the runtime of this algorithm is cubic in the number of states. In a Markov chain with n states, to remove one state, we have to look into n predecessors as well as n successors, and we have to repeat this for n minus 1 states, leaving us with a cubic runtime. So let's see how we can utilize tree decompositions to solve this more efficiently and linearly. Assume that we're given a Markov chain C and a target vertex V to which we would like to compute the hidden probabilities. We are also given a tree decomposition T, which is going to basically help us in finding an ordering of vertices to be removed from the Markov chain using the state elimination trick. So let's see how it works. At each step, we're going to choose a leaf bag. For example, here, we could choose this bag, and this bag, while we have chosen the blue bag. And within that bag, we're going to choose a vertex in a way that that vertex is not present in the parent bag. For example, here, vertex 9 is chosen and also shown in the corresponding initial graph. Vertex 9 is not present in the parents. And we're going to simply remove vertex 9 using the state elimination trick that was just mentioned. Note that the reason that we're going to choose a leaf bag and within that leaf bag we're going to choose a vertex which is not present in the parent is the fact that this is the only bag that this vertex is present in. Because we remember that in tree decompositions, the bags that contain the same vertex form a connected subtree. So this is the only bag within which vertex number 9 is present, and we know that in each bag we have at most t vertices, and in this bag all the predecessors and all the successors of vertex 9 are present. So in order to fix the probabilities from predecessors to successors, we have to make at most t2 computations. Vertex number 9 has been removed, and this bag has only vertex number 7, which happens to be present in the parent bag. So we will simply discard this bag. Again, we choose a leaf bag, and within that leaf bag we choose a vertex which is only present in this bag and not the parent, meaning that this vertex is only present in this bag and not any other bag within the tree decomposition. Finally, we remove that vertex and proceed. The leaf bag containing vertex 5 and 6 is useless and thus removed. A leaf bag is chosen and vertex number 5 from that leaf bag is chosen to be removed. Again, we have a useless bag which is discarded. we choose a bag, we choose a vertex from that bag, and we remove that vertex from the Markov chain. That bag becomes useless, and we discard it. We choose a leaf bag, we choose vertex number 4 from that, and we remove vertex number 4. The bag becomes useless, and we discard it. We choose the only leaf bag, and we choose vertex number 1 from that leaf bag, and remove it. The bag becomes useless, and we discard it. Vertex 3 is removed, and we're left with only vertex 2 and 6, for which we can simply compute the hitting probability. Now, to compute the hitting probabilities for other vertices, we can add them in the reverse order of removing and compute the hitting probability from the successors. As mentioned before, we perform at most T2 computations to remove each state, so in general, the runtime is linear in the number of states and edges of the Markov chain. This algorithm was for computing hitting probabilities. However, other objectives such as mean payoff and discounted sums of rewards can be computed in an analogous manner. These speedups are extended to MDPs using a strategy iteration. In that case, we will fix the MDP's strategy using the strategy iteration and transform it to a Markov chain and compute the hitting probability or other objectives in the manner that was just mentioned. We have implemented these approaches in C and performed comparisons against well-refined model checkers on the DeCapo benchmark suite. The DeCapo benchmark suite consists of real-world Java programs and their control flow graphs. The MCs and MDPs are constructed in a semi-synthetic way from these graphs by associating random probabilities to edges for Markov chains and randomly splitting the vertices to action and choose vertices for Markov decision processes. For this case, hitting probabilities in Markov chains, Prism model checker, Groovy optimizer, MATLAB, and Storm model checker, as well as an efficient implementation of the Gaussian elimination have been used. The blue graph indicates our approach. Note that the runtimes are in logarithmic scale. For the second case, expected discounted sums in MCs, not all the previous approaches support this kind of query. And for Markov decision processes, computing the hitting probabilities is demonstrated here. As you can see, our approach consistently beats all these other highly refined and optimized tools by one or more order of magnitude. And finally, computing expected discounted sums of rewards in Markov decision processes. Thank you for your consideration, and please feel free to reach via email if you have any questions or comments.